Okay, so hello everybody. I'm Markus. Thanks for coming to my talk. I know that after 3 days of conference, it's especially hard on the last day. So thank you for that. And my talk will be about free versus tagless. So maybe a quick show of hands who has ever used a program with a free monad. Okay. Who have ever used final tagless? Anybody? Okay, perfect, because we will go from the ground, so you will just know about it afterwards. So here's what we go through. So most of the talk is based on Oleg Kiselyov's excellent paper about free and final encodings, which we will go through at the start. So we will clarify what tagged means, what tagless means, and what initial and final means. We will talk about how to extend our languages that we will write in a moment, how to inspect and transform the programs written in our DSLs, what the free X and MTL style is, and how it compares to the initial and the final encoding from the paper. We will compare both approaches, and also I will be using Scala syntax. So who's familiar with Scala syntax? Just so I know how much to explain. Okay, that's quite a lot. But the ideas are basically independent, and for example, the final encoding can be implemented in any language with type classes. Okay, so here's the link to the paper. I also have a reference slide at the end, so you don't have to write this down now. What we will be building in all of the case studies that will be coming is a small toy language that has some operations. So we are able to have integer constants that look like this. We can have integer addition, so we can just add two integer literals. We have string constants and string concatenation, and we are able to convert from a string to an integer using our language. Okay, so let's start with initial versus final and tagged. So in the paper, Oleg introduces the two approaches, and he calls them initial and final. So that's where the name comes from, the final tagless encoding. That's from this paper. And the initial approach defines your DSL as a value, and you deconstruct it using pattern matching. That's the basic idea. And in the final approach, shown here, we have a set of combinators that are just ordinary functions. So that's the whole idea between initial and final. One is having your program as a value and using pattern matching, and final is just having combinators and functions. So let's start with the initial tagged version. So just as a reminder, we have our small language, and we want to be able to run programs that in Scala would look like this. We can add integers, we can concat strings, and we can convert to integers. So here's an ADT that reifies our language. So we have basically it's an ADT in Scala. So for those of you who don't know Scala, it's an ADT in Haskell. And we have the name is expression, and we have different cases for the integerals, the string literals, the integer addition, the concatenation, and the string to int. So it's basically a straightforward translation of our program language. And with this, we can by hand construct a program that concats two string literals and then converts the whole thing to an integer. So this is a more readable representation of this. The problem is that we are also able to construct programs that don't make sense. So we can also write string to int of an int literal, which doesn't make any sense, right? It's already an int. And it's not a string. So we have our expression ADT. Now we want to write an interpreter, and this is like the theme will continue over the presentation. We will always be writing the expression and then an interpreter to interpret our language. So here's the first initial tagged interpreter. Given an expression value, well, we can pattern match on it. This is the initial approach. If it's a literal, we return the literal. If it's a string literal, we return the string. And the problem is, first of all, this is an int and this is a string. So the return type cannot be value in every case, and then we would have any. And we also have cases like the add has a string literal here, so it's an invalid program, so we have to take care of that. So this signature doesn't quite match what we want. So instead, we need to introduce a result type, which is an ADT again, which is either an integer or string, because our language supports integers and strings. And then we can write our interpreter, we pattern match again on the expression, and we just tag the result value with int result, string result, or we delegate to some internal helper methods. For example, in the addition case, we get passed in the two expressions, we interpret both. If both are an integer, everything is fine, we can just continue. And otherwise, we get an either left, so we just add a string that says, I cannot add those two expressions. Maybe you did an error while constructing the program. Okay, so this is basically the whole idea of the initial tagged version. We have a program as a data structure, which is just an ADT, and we deconstruct it doing interpretation using pattern matching. The problem of this approach is we have to handle the errors in the interpreter, whereas it's actually an error during construction of the program. So it's too late to handle the error. And by the way, this is a very nice criteria for any DSL, so it should not be possible to generate false programs. Otherwise, it's a very flawed DSL. Okay, so as I said, this is the initial encoding. This is also where the tagged name comes from. So if you think about finally tagless, this is the initial tagged version because it's the initial for the data structure, and the tagged because we have this int result tag to have the result, the actual result. Okay, let's go from the tagged initial to the tagless initial encoding. And we saw the problem of encoding invalid programs. The next step is to make them impossible. And to do this, we can use a construct that is called GADTs. And what we do is we have an ADT again, but this time it has a type parameter. And the type parameter can be refined in the cases. So the int literal refines the type parameter a to be an int. And the string literal refines it to be a string. So whenever we construct an int literal, we know that it's an expression of type int. So we have more type information now. So we can again construct our program the same as before, but the invalid one will not compile. Because the string to int, if we look back, the string to int as an input wants a string. And this is just not a string, it's an int literal. And during interpretation, we again just pattern match on our expression case. But when we pattern match, we recover the type parameter information. So you can see here that we get passed in an expression of type A, and we return a type A. So when we pattern match on the int literal, the compiler knows that the A has to be an int. So the interpretation of an expression int program returns an int. So in each case, we just recover the type information and everything will work out. That's the magic of GADTs. And the handle at case is actually a lot more simpler now because we don't have to do any error handling. If a program can be constructed, it's correct. So we just have to interpret both sides and add the two integers. Okay, so to recap, we may use GADTs to make incorrect programs impossible. So we can get rid of the either during the interpretation. And this is also why there's basically no reason to ever use the initial tagged version. You always use initial tagless if you have GADTs. It's just not that much better. Okay, so that was the initial approach. We had two initial approaches, the tagged and the tagless one. And now we go to the final tagless approach. So final means we avoid the data structure. So there is no ADT of our program. Instead, what we have is a type class for the operations of our DSL. And then we have instances for the concrete implementation. And the interpreters will just be instances, as we can see in a moment. And you also get type safety out of the box, so there is no tagged version at all. There is no final tag, there's just final tagless. Okay, so our language, which was previously an ADT, now looks like this. It's basically the encoding of a type class in Scala. So we have a type class called expression sim, that is parameterized over a higher kind of type constructor, which I just called expression for the familiarity. And we have cases for all of our language constructs that have been in the ADT. So we have the intlet case, the stringlet case, the integer addition, the string concatenation, and the conversion. And we can write a sample program with our DSL by saying we require the higher kind of type constructor, which we are parametric over, to have an instance of our type class. So we say whatever f is, it needs to have an expression sim instance. And then just to avoid the prefixing, I imported everything from our input argument. And then we can write normal programs like this, which almost looks like the ADT version, just with lowercase names. And everything is just calling functions instead of building up a data structure. Okay, and now we have to interpret this somehow. And as I said, the interpreter is just the instance of the type class. So let's add a new type called int_p, for which we define the type class instance. So we say implicit val, that's how you do a type class instance in Scala. And then we implement the expression sim type class. And we say for the int literal case, we would just wrap it up in the int_p value, which is generic over a. In the addition case, we add the both values and then wrap it up. And the same for the string concatenation. And in the string to int, we just call dot to int. Okay, so that's basically the whole idea behind the final tagless encoding. You just have the type class and the combinators for your functions, and the interpreters are instances of this type class. So this was the basic thing. So if you have any questions, you should probably stop me now, otherwise it will only get more confusing. So if you have any questions, yes?
I'll be the slow person in the room. I'm with you to the tagless, I got it.
Yeah.
Final tagless, I'm not there.
About the general approach, or okay, so
you put all these operations in go back a couple slides.
Yeah, so you mean all of the operations from the ADT here?
Put all the ADT stuff into
Yes.
what?
So this was the ADT,
Right.
and then we have a type class here, which for each case of the ADT has a method. So we had an intlit case in the ADT, we have an intlit method here. We had an add case in the ADT, we have an add method here, and so on and so forth. And then, when you write an interpreter for your program, you instantiate the type class. So you just override all of the methods, which is something that's actually done. And in this case, we perform the addition, the string concatenation, and the integer conversion.
Do those slides posted anywhere?
I will post them afterwards, yes.
So does this mean that some of the type class methods are actually unimplemented when they don't make sense with their...
They have to be implemented.
So you've only got add for integers, you haven't got add for strings, so how's that?
Add only takes an integer, so there is no way to add to strings. I have concat for strings and add for integers. There's no way to pass a string to the add.
Okay, so they're, despite the so it's not interprets the instance, it's interprets the instance, not int. So it goes
No, it interprets into the int_p value.
Right.
Because that's what we instantiate this one with. So if you see here, the stringlet value returns an expression of string. And in this case, we replaced expression with the int_p.
Right.
So we would return an int_p of int, an int_p of string, and we just unwrap it with dot value.
Can you say again what tag and tagless actually is referring to?
Yes, of course. So the tagged one refers to this one here. So you need this result type in order to represent the result of the interpretation here, because sometimes it's an int, sometimes it's a string. And you need to have a return type, a single return type for this.
So it's the term tag refers to the fact that it has a result type?
So tagged, there's a term in type theory that is called tagged union, which is another name for a sum type. And we have here a sum type for our result, and this is a tagged union, so this is the tagged approach.
Got it. Okay, that makes sense. Thank you.
Yeah,
So in the initial case, the program is kind of stored as data.
exactly.
And in the final case, is it fair to say the program is stored in a call graph?
Exactly, yeah, that's a good way to point it. So maybe to repeat it, in the initial approach, the program is stored as data, and in the final approach, it's more or less only present in the call graph. There's no program, there's just the call graph of your combinators. Okay, good questions. So if any of you have been to Tony's talk, you maybe already know the expression problem. Here's it is again. So the expression problem was coined by Philip Wardler some time ago. And it basically handles the problem that you have a data type and you want to extend it. And you want to extend it by adding new cases to the data type, and you want to add new functions over this data type. And you want to do both of those things while not touching any existing stuff. So you don't want to be forced to recompile existing stuff. And you still want to have type safety. That's the basic idea of the expression problem. And now let's see how our two approaches solve this. And the first case study for this is we want to add a pretty printer for our language. So instead of running it and reducing it to a string or an int, we now want to print the whole program. And in both cases, we just have to add a new interpreter. And let's start with the initial encoding. Okay, so the initial coding makes this pretty easy. We just add a new function that takes an expression value and returns a string. And we do this by pattern matching on our ADT again. So we get an expression of A, and we return a string. That's our pretty printer. If it's an int literal, we return a string that represents an int, and we do the same for the string literal. If it's an add case, we pretty print the left-hand side, interpolate this into the string, pretty print the right-hand side, interpolate this, and then render a nice string for the whole program. And if we now have our sample program that just adds two strings and converts it to an int, we put this into the pretty print, and we get out a nice little string that represents our program. So in general, adding interpreters in the initial encoding is easy. You just add a new method, pattern match on it, that's it. But what about the final approach? Well, in the final approach, the interpreter were just instances of the type class. So here, adding an interpreter means adding a new instance for the type class of expression sum. So previously, we had the interp case class. Now we have the pretty printer case class. And for this case class, we add a new instance of the type class expression sum and instantiate it to pp. And for the int literal, we again just render it to a string where we have the value interpolated here. And for the addition case, again, we interpolate the left-hand value, the right-hand value, and everything is put into a string with a plus in between. And if you look at the sample program again, it's the same sample program as in the other version. We can call sample program where f is instantiated to pp, which means that we pick up the instance for the pretty printer. And what we get is, if we unwrap the value, is the string of the pretty printed program. So even though there is no actual data representing the program, we can use this instance to just render everything to a string. Okay, so as I said, adding a pretty printer for the final encoding is also just adding an instance for the type class. And in both approaches, there's no need to touch any existing code. And in general, final Tagless supports the introduction of new functions of the data type just as well as the initial encoding. There's basically no difference. Both work very well with this. So let's go to the next case study. Let's try to add if to our language. Oh, and by the way, the first one in terms of the expression problem was adding a function over data type. And the if case is the other one. We just want to add, we want to extend our data type with a new case. Okay, so we need a way to introduce Booleans to our language in order to if on it as a condition. And we need the actual if construct. So with the initial encoding, we have the ADT. And we just add two new cases. One is the Boolean literal, and one is the actual if case. So the Boolean literal just refines the A to be an expression of Boolean, and the if one is parametric over the two branches of our if. Okay, so we can just go straight ahead and add this to our ADT. Yes?
But since the expression is CO, we have to add these case classes in the same file.
Yes. So this would already break the expression problem. And we just break it, and I will show you a way how to avoid it, but it's a little bit more involved. Okay, and then we can write a sample program. It's where we just call an if with a Boolean literal of true, and if true is true, then return 42, otherwise it's 21. And now we have to touch our interpreter because we extended our data type, and our interpreter matches on all instructions. Yes?
Do we have to touch the interpreter? Couldn't we have a different interpreter that wraps this, that just handles the new cases and that has a wildcard that has all other expressions?
Well, the problem is that you will get a warning that the other interpreter is not exhaustive. And if you do something wrong, then it will just break with an inexhaustive pattern match.
Okay.
Yeah, that's why you can't wrap it. Okay, so we need to touch our interpreter, which matches on all cases. And we added the bullet case, which is easy. And for the if case, we just add a new helper method that handles the if one. And what it does is it just calls the actual if from Scala. We interpret the condition, and if the condition is true, we return the if true condition, which is interpreted, and else we interpret the false condition. Okay, so this is basically what the expression problem is all about. We had to touch the data type, we had to touch the interpreter. So if you imagine that you have a lot of interpreters or a lot of cases where you pattern match on your data type, this is a big mess. So if we regularly extend our language, we will get in deep trouble. And it would be better if we could just compose our language like having an if language and having our toy language and just composing them together. And the initial solution to this problem is called data types a la carte. And this is an actual paper by Wouter Strijstra. You can look this up. And the basic idea is, if you know recursion schemes, it uses expression functors. So your data type is no longer a normal data type. It's parameterized over yet another type parameter. And then you will build the fixed point of your data type, basically. And there's machinery for this in cats, where you can inject your languages into some coproduct. And there's a lot of heavy type level machinery to do this. And in summary, this is normally a big pain. And you probably don't want to go there unless you have a good reason. Okay, so I won't do this in this talk, but just keep in mind that for the initial case, you can solve this problem with data types a la carte. But let's compare it to the final tagless version. So let's add if in the final encoding. So what we do is we create a new type class that is independent of our old one, which is called expression if. It's again parameterized. And we just add the Boolean literals, and oh yeah, I added the into bool conversion as well, just to make it more fun. And we have the if expression as well, which has the if true and the if false condition, and is here, yeah.
Why are your two halves of your if functions rather than expressions?
Why am what?
Why are they lambdas and not just expressions?
Oh yeah, they are lambdas because for the if you normally would expect the two condition of the branches to be only evaluated when it's true or false. So if it's true, and you can make this a little bit less explicit by using by name parameters, but it's not easy to do this in case classes in Scala, and this is just more explicit for the caller that it's lazy. So we only want to evaluate the condition, if the true branch, if it's true, and otherwise the false branch. That's why it's functions. Okay, so we have our new type class, and now we can write a program, and instead of just saying our f has to have an instance of expression sym, which was our old language, we now say it also has to have a type class instance of expression if. And if we import both of these just to make it available without a prefix, we can write a program that looks like this. We have a string literal of 42, convert this to an int, convert the integer to a bool, and write an if expression that, based on this condition, it says either it was true or it was false. So just as a reminder, we didn't touch any existing code. We just wrote a new type class, and now we can write a new program that uses both languages. And there was no magic involved. And we also, for the interpreter, we don't have to touch any existing code. We can reuse our interp case class from the previous slides. And we just add the two cases for the boolet, or for the three cases, the boolet, the into bool, and the if expression. So I just arbitrarily said that any integer that is 0 is true. And for the if expression case, we just interpret the condition, c.value, and otherwise we continue with a true case, and if it's false, we continue with a false case.
Can we go back one slide?
Yes.
So, if I'm understanding this correct, the magic here of getting all this stuff for free, is that implicit there? Is that correct?
Yes, so the magic to get this for free is you have just the two type class instances here. And given that both of them refer to f, which is our single type constructor that we are parametric over, they say that f has to have both capabilities of those languages. And that means they will just work together without any problems.
Just one question.
Yeah.
The tagless example, there were not only one expression? We're not adding to the if condition to the same algebra?
There was only one expression.
Not on the final tagless, sorry. The other example.
You mean the initial one?
Yes, the initial one, when you're reading the if.
Oh, you mean why there are more than one?
To me, it's quite different here. The if is part of the same algebra. On the other one, you're separating the type classes.
Oh yeah, I just separated it. You mean the parameters, right?
Yes, and also how you evaluate the expression you have to do separately. If you don't have to do it.
I just.
No?
You mean the multiple parameter lists or something else?
What?
Do you mean the multiple parameter lists or something else?
No, I mean how you evaluate the expression here.
Oh yeah. You mean in the interpreter,
Yes, exactly.
where I just do c.value here.
Yes, exactly.
So in this case, we know that for the if expression, our condition is of type expression Boolean. And expression is the type parameter here. So if we instantiate this with inter p, so in this case, let's start here. So we have this f, and we know that this is a f of Boolean. And in the other case where we say interpret this, yes, so we say f is inter p, and the inter p has the .value method. So our f Boolean, which is here, is an inter p of Boolean. So it's already a Boolean. I have to unwrap the case class because there is no data tree constructed, it's just a call graph. It's actually already a bool. There is no other way. So we don't have to recursively call our interpreter. That's probably what confused you. Does that help?
Can you show the previous example, not the final that's the other one, when you were doing the evaluation?
This one,
Oh,
where we handle the if condition and we interpret the condition.
okay, yes, he was separate. No, it is separate.
Okay, fine. Okay, but any other questions before we continue? Yes?
Can you use functions from the other interpreter in this interpreter or not?
What do you mean functions? You mean the boolet and the other cases? Intlit?
Int to string or string to int?
Yes, that's basically what I did with the example program, right? I just used the string to int and the stringlet and the int to bool together.
But that's in the example program, not in the interpreter.
Yeah, so the interpreter is just the instance of the expression if class. I could also do new expression if with expression sum, but we already have the expression sum for inter p. We did this already. So we don't have to do this here. So we cannot use any of the other math functions here. They are not available. Okay, so yeah, I could, exactly. But then I would have to touch the existing code. We want to keep them separate. And that's basically the big advantage of final Tagless. So we had our existing interpreter for the base language, and now we added a new case to the language and a new interpreter, and we didn't have to touch anything. So in this case, final Tagless solves the expression problem very neatly, in my opinion. And we didn't have to go through all of the hassles of data types a la carte. So if you ever try this, you will really appreciate the easiness that we have here. Okay, so to recap our case studies, in the initial encoding, it was easy to add new functions, but it was hard when we extend the data type. Then we'd had to resort to data types a la carte. In the final encoding, however, it was easy to extend both the language and add new functions. So if you need extensibility in both dimensions, go for final Tagless. Okay, so this was 2 case studies of extending our language. Let's see what we can do with the programs written in the DSLs. Maybe we want to optimize the programs, maybe we want to transform them. Those are both valid cases. And basically in the DSL, the point is that the programs are written once, but interpreted many times, maybe with different interpreters, maybe they are pretty printed, maybe they are analyzed, whatever we want. And there's this myth that in final Tagless, because there is no program, it's not easy to transform it, because there's only this call graph, right? But we will see that it's actually not like this. So what we want to do as an optimizations that I've come up with is we want to inline addition of literals. So whenever we have in our tree an add with 2 nodes that are literals like this, we want to go over a program and just replace this with the added literal. So we just do some partial evaluation of our program basically as an optimization. So this is the optimization that we will be implementing with both styles. And if you just remember in the initial encoding, we are building the tree and we use pattern matching to deconstruct it. So our actual program in the initial encoding looks like this. We have the add case class with another add case class with the two literals, and on the right-hand side we have the string to int of the string literal. This is our actual program that we will have. So what we can do is we can write an inline addition function that takes the program expression of A and returns the program expression of A. And what we do is we just pattern match on the program. And given that we can nest in the pattern, we can say if it's an add node that has two literals, we just inline the literal. Otherwise, if it's a normal add case, we just recurse down. And in the other cases, we just leave the program unchanged. And this is just one step. So maybe there are many add nodes. And by inlining one, we could create a new opportunity at the top level. So we have to do this as a fixed point. So we have to apply this as long as our tree changes. And we only stop when it does not change anymore. That's basically all we have to do in the initial encoding. We just have to pattern match on our program. If we spot an opportunity to do something, we do it. Otherwise, we don't. And it's easy because we just have the ADT. But now let's look at the final encoding. As I said, in the final encoding, there is no program. There's just this call graph. And we cannot do any pattern matching on the AST. So the trick here is we need to make our context explicit and then write a specially crafted instance. And in our case, we need to keep track of our predecessors. So this is like the first approach on how to tackle this problem in the final case. And the idea is that when we traverse the tree, so we start at the top, then we go into the left add and to the intlet, then we go up to the add, down to the intlet, up to the add, up to the top level, down to the string to int, and down to the stringlet, and then bubble up again. So what we end up with is a predecessor list during the traversal that looks like add, intlet, add, and so on and so forth. And now what we could do is when we see something that looks like, so we are here, and our predecessors was an add with another intlet, then we could just optimize this part because we know that this one is just an add node with two intliterals. Okay, so in order to do this in the final encoding now, we add a context ADT. So this is just to keep track of what we have seen previously. It either was the context of an integer with some value, the context of an add node, or something else we're not interested in. So this is basically the same like in the initial encoding, we only match on the intliterals, the add, or underscore for the rest. And our other is just the underscore. We don't care. And then we add a new case class that we call opt, which is our optimizer. And this is a function that, given a list of contexts, it returns a tuple of a new context and the actual interpreted value. And we actually are abstract over this f parameter, so this could be any base interpreter. It could be our pretty printer, it could be our actual evaluator. And then we add a new instance to our type class expression sum for our opt case. So we do an expression sum of opt, and we have some base interpreters, so this f1 has also an instance of expression sum. So we just wrap some existing base interpreter. Okay, so the instance is a little bit more involved now because we have to do all of the context checking. So here's just the intlet and the add overrides. I did not include the rest of them. In the intlet case, what we do is we have to create a new opt of int. So we have a context and we just add, oh, we are currently looking at an int literal because we are in the intlet method. Prepend this to our context and call the base interpreter's intlet on the value. So this is pretty simple. What happens in the add case? First of all, we start with the context 0. We pass this context down the first interpreter. So we go to the left branch and we prepend that we are currently looking at an add node. We get back a new context and a value of the left-hand side. And we use this context 1 to pass it down when we traverse the right-hand side of the add node. So we add, again, that we are currently at the add node, traverse down the right branch, we get back our final context and our value for the right branch. And what we can then do is we can pattern match on the context list. If we have seen that we were looking at the context int, and above this was an add node, and then context int again, and the add node from going up, then we know we can do our optimization and we can inline our literal. So what we do is we extract the left-hand side and the right-hand side, add this to our context, and then call the base interpreter with the optimized value. And in all of the other cases, we just keep our context as we are looking at an add node. So here we change the context to an int. Here we keep it as an add node and call the base interpreter's add method. So this is the whole optimizations. In the one case, we call the base interpreter with the intlet, and in the other case, we call the base interpreter with the add. That's how our inlining works. Okay, I know this is quite complicated and it's late, but just trust me that this works. So in general, in the final encoding, the problem is that you have to make the whole pattern matching context explicit. So here we had to keep track of our predecessors, but it's non-mechanic. Sometimes you have to come up with some clever way. And all of this just because you lose the pattern matching from the initial encoding, which is pretty powerful. But you can still do every optimizations in both approaches. So when you can do it in final, this means you can also do it in initial and vice versa. Some things are just really, really hard. For example, serialization and deserialization becomes very tricky in the final encoding. And also during every inspection, you will have to run the program. For example, in the pattern matching case, you can put a deeply nested pattern, but in the final encoding, you would have to run the program in order to get to this deeply nested state, which can have some overhead. And if you paid attention, actually this is just like an encoding of a state monad, what we did, because our opt case was just from some state to a tuple of a new state and some value. So you can also do some tricks with the state monad there. But actually our interpreter has a very, very subtle problem, which I don't think anybody noticed because it's late, unless somebody was really paying attention. Didn't guess so. So the problem is we always traverse the left branch because we only know that it was an add with two inlet cases when we get down here, get up again, and then at this point when we go down here, we know it. But that means we already called our interpreter with this one, which may be bad for a deep tree. So we do unnecessary work, and maybe if there is an effect, we even run effects we don't want to run. So what we should do, like in the initial encoding, we should look ahead instead of traversing down and then knowing from the predecessors that we want to do something different. And we can do this by writing an even more clever instance. I actually did this. If you want to look it up, it's on the repo, or you can ask me afterwards. Okay, so this is basically how we work with programs in both encodings. So in the initial one, it exists explicitly as data. It's easy to pattern match on. It's cheap to inspect and transform. And in the final encoding, our programs are just functions with the call graph. And while inspection and transformation is still possible, it's more work. But you can still do it. Yes?
It seems almost like in this example, in your tagless, you just created the tagged tree and then manipulated it. You didn't quite.
In the first optimization, exactly, yeah.
You sort of just used one to emulate the other.
Yes, so in the first optimizer, I basically reconstructed more or less the tagged, or in the initial encoding. Yes, but this is a very common theme for the optimization case because it's just nicer to express it. But I think there are probably other solutions. It was just what I came up with. Okay, so we talked about initial and we talked about the final encoding, but the talk was about free versus final tagless. So where does free and also MTL come into play? And actually the free is just an initial encoding because you have your code as a data structure. But a free X, so for example, a free monad is not only your language, it's your language from the initial encoding plus the type class and its laws. So whenever you have initial encoding of a language and you do it in a free monad, that means your language gets monadic power. And of course, you don't have to choose the monad. You can also choose a free applicative, a free monoid, and whatever. So initial encoding plus DSL based on the type class. That's what you get from the free. And we can write our language again using the free monad. For this, we just have an expression f. And this time, we don't wrap our arguments into this expression f. They are just unwrapped. They are normal integers. And the monad key will be the one that is responsible to extract, for example, the int from an expression in f int. And what you normally do with a free monad, you create a type alias that is then the free applied to your expression functor and some result value. You add smart constructors for your cases, so you do the injects in every case. And then you can write a program that uses flat map. So you have your stringlet 4, and we flat map over this, and stringlet 2, and flat map again, and we concat this, and then we have a result. And that's how we can write a program with free monads. So what's nice about this is that we can suddenly use all of the monadic functions that exist. So we can also use an if value, because on the left-hand side we have the unwrapped value. And we can also use combinators like replicate or monadic ifs, whatever we want. And the interpreter now uses, again, pattern matching on our ADT. And there's a special function for free monads here that is just called fold map. And it takes just a function that matches on a single instruction, like intlet, add, stringlet, and so on. And we just interpret the add with the actual addition and the stringlet by unwrapping the value. That's the basic idea. Okay, so we use the monad to embed our language, which is then responsible to extract the real value at every step. What's nice is that we get interoperability with Scala, and there are lots of combinators already existing for monads. The only bad thing is the interpreter will fix sequential evaluation. So beforehand, we could, in theory, traverse both branches in parallel. Now we are fixed to flat maps, so flat map is sequential. But again, this is just an example. Instead of the free monad, you could have used a free applicative or something else, and you would have more power. Okay, so this was the free as an initial encoding. There's also an approach called MTL, which originally comes from the monad transformer package in Haskell, which defines type classes for monadic capabilities, like accessing state is a monad state, accessing reader is a monad reader, and you just have a type class for it. And this is commonly referred to as MTL style by now. And I would claim that this is basically the final Tagless encoding with the addition of type class ops. So you have the free data structure that adds the type class thing to your DSL, and here you have a type class constraint on your DSL that adds the power in the final encoding, which should sound familiar. So if we have an expression sim language, first of all, we also unwrap all of the arguments. And we don't, and then we don't unwrap in this case in the old one, so this is without MTL. And if we go to MTL, we unwrap all of our arguments. So beforehand, this was expression int. And now this is just an int because the monad takes care of that. Yes. And in our sample program, we can just write the monadic style again. But the difference is we require a monad instance for f. That's all we have to do. We don't need a free monad data structure. We don't need a free x data structure. We just require a type class instance on our f in addition. And suddenly we can get monadic DSL. Of course, what we have to do is we need to write a monad instance for inter p now. But this is also pretty easy because it's just the identity monad in our case. But you could also just use something else like future or whatever you want. And the interpreter is basically the same as before. And we could leave this almost unchanged if it wasn't for the unwrapping of the arguments. Okay, so again, in the final case, the sequencing is no longer part of our language because the monad takes care of this. We have a very flexible choice of our target monad now. We could interpret into a future, interpret into a task, interpret into an option, whatever we want. And we can also choose between type classes easily. So if you write a program in the free monad and a program in the free applicative, there's no easy way to mix both of them. You either have to translate the applicative to a free monad, or you have to do some tricks like embedding the free applicative into some free monad case. But with the final case, you just can have a program with an applicative type class requirement and a monad type class requirement, and it will just work out because the two constraints on the implicit type classes will just work due to inheritance. So it's easy to combine two programs that are written in different styles, which is not the case for the free approach. Okay, so the level of introspection on programs written in both styles heavily depend on the choice of your type class. If you require a monad, you will not be able to inspect any of your program because you only can look at the first instruction and the rest is hidden behind the flat map function, and you cannot look into that function. And this is also why if you need a monad constraint, you never want to use the free monad. You always want to use final tagless. It's more performant. You won't be able to inspect your program anyway, so just go with final tagless. Which brings us to the comparison section. So we've seen both approaches. So we have seen the initial encoding and the final encoding. But the important question is when to use which. And of course, as always, the answer is it depends. But first of all, there's a neat little thing, so I will just go over it quickly because of time, but you can convert between the two encodings. So you can go from final to initial, and you can go from initial to final. So you can transcode your program that is an ADT into one that is a call graph, and vice versa. Which means you can write your optimizations in the initial style using pattern matching. And if you want to apply this to a final program, you can translate it first to an initial encoding, apply the optimization, and then go back to the final encoding of your program, which is pretty nice. And this is basically the overview. So if you have the initial tagless encoding, your programs are first class. It's easy to add interpreters, but it's hard to change your language. It's really, really hard to compose different languages. It's easy to optimize, transform, serialize, partially evaluate, pass around as arguments. But if you need a monad, you should use final tagless. If this is the only thing you keep in mind from this talk, then keep this in mind. There's always a structure that is built up and torn down again. So this has overhead during your evaluation of your program. For example, if you use a free monad, you build up this tree, and then you traverse it and tear it down again. Of course, the initial encoding requires GADTs for type safety. So if your language doesn't have GADTs, you're more or less screwed. And basically, my recommendation is use the initial encoding if you inspect your programs much more often than you run them. And for the final version, passing around programs can get very tricky because they're not first class. It's easy to add interpreters, and it's also easy to extend the language, and they compose naturally. It's very hard to optimize, transform, serialize, partially evaluate them, but you can still do it, as I've shown. You have a very flexible choice using the type class constraint. The execution is faster because there's no intermediate structure that is built. So if you only run your programs and maybe inspect them once or twice, you should go for final tagless. Okay, so this is basically the conclusion of my talk. This was an overview of final and tagless encodings. This is wrong. Overview of initial and final encoding. We went from tag to tagless. We went from initial tagless to final tagless. There was a relation between the initial, final, and free and MTL. We talked about some optimization and introspection of programs, and I gave you some guidelines on when to choose what. And that's the end of my talk. Thank you.